Welcome to Hot Chips 31. Session 3, Methodology and ML Systems.
Hi, next session is Methodology and ML Systems. I'm Yoshimasu Butch from Tosho Memory. Sorry about my voice. I'm having a problem with my vocal band, so I hope you guys hear me okay. Our first speaker is Keyi Zhang from Stanford University. He talked about Agile hardware design methodology. Keyi is a PhD student in computer science at Stanford University. His research focuses on computer architecture and machine learning. He's a member of Stanford AHA, Agile Hardware Center, a project that aims to explore hardware design, agile methodology, and making hardware design fun again. Sounds good? Okay.
Hello, my name is Keyi, and I'm a member of Stanford AHA Agile Hardware Center. Today, I'm going to present our research on creating an agile hardware flow. Let's briefly review how hardware design, especially hardware accelerator design, is being done today. First, the designers usually start with a set of applications and trying to figure out what kind of computation flow can be accelerated. For example, it's very popular to look at those machine learning models right now. This kind of studying application process typically involves with creating or finding tools to model the application performance, to figure out the best microarchitecture. This is a process usually called design space explorations. Once a best microarchitecture is being found, the designers usually write down a design specification or simply spec to describe the design. Next, the hardware engineer is going to implement the spec using hardware description languages such as Verilog or System Verilog. Right now, there's a growing trend of people trying to use either high-level synthesis or even generation framework such as Chisel to produce some building blocks. Those designs typically incorporate external IP blocks provided by vendors such as Cadence or Synopsys. Once the hardware interface is being decided, the software engineers are going to write softwares such as firmwares, drivers, and compilers to support the hardware as well as applications running on top of those toolchain. Those kind of design flow, as we discovered in software engineering, is called waterfall because we have a linear stage design flow where each stage depends on previous stage. For example, in the hardware design, we depend on a fixed written documentation, and in software design, we depend on a fixed hardware interface. So those kind of design methodology, as we see from the software engineering, has one fatal problem, which is the failure to deliver product in time. There are lots of root causes for this problem. For instance, it may be caused by change of application requirements, or due to incomplete knowledge or understanding of the problem. In the context of building hardware accelerators, because we change application requirements, that means that your accelerator may be mistargeted. Or simply due to misunderstanding of the hardware constraint, the performance model used to model your application during the initial design phase may be invalid. Now the question is there an agile approach to hardware design? Hardware design usually takes months and millions of dollars to produce. Is there any way to avoid the shortcomings I just mentioned? And if it's possible, what are the requirements or toolchains to enable the agile hardware design? At Stanford, we believe there are two major requirements to enable agile hardware software design. The first requirement is to maintain an end-to-end system that supports continuous integration and deployment. That means that we had a system that keeps track of problem domain and let users to see the values in the system in a very early stage. In the context building hardware accelerators, that means you have to map application to a running hardware as soon as possible. If you look at the picture below, that's the software system we'll be maintaining at Stanford. So we constantly feed applications into our hardware and software compilers, then execute it through simulation, emulation, even on devices through the early designs. After execution, we can fix the bugs and collect the performance metrics, which leads to the second requirement, which is the ability to evolve the system to make it more efficient. Because we are in Agile hardware design, the initial system won't be optimal. They have maybe some lot of bugs and other stuff. But the idea is that to individually improve each component so that the overall system will be more efficient. So the improvement can come from the application. For example, we can just simply use more efficient, more accurate machine learning models. All the changes can happen in the software compiler. For example, we can improve our compiler to have much better memory blockings to leverage memory localities. Or we simply find a much better microarchitecture for our hardware. Those two requirements sounds very straightforward, but the question is, why it's hard and why no one's doing that today? So there are a couple actually very challenging problems based on those two requirements. The first is that with a fixed hardware, we can continuously optimize applications. For example, we've been enjoyed ever-improving compiler techniques, but those compilers typically are built on top of assumption that the underlying hardware is fixed. For example, we have relatively stable Intel x86 instruction set. The problem with Agile design is that we don't have a fixed hardware, so we cannot make assumption that the hardware is fixed. Similarly, if we have a fixed set of applications, we can just go ahead and extract those key application parameters and use those parameters to drive the design space accelerations. And again, because applications and compilers are always changing to be more performant, we don't have the luxury to have a fixed set of applications. At Stanford, we believe that if we carefully define the interface between different stages, we can actually avoid the problems I just mentioned. So for example, we use Halide as an interface between applications and compilers. Halide is a programming language that provides a complex set of hardware scheduling primitives. People have been using just scheduling primitives to fine-tune the application performance on CPU and GPU. So we believe that if we carefully reinterpret the hardware scheduling primitives in Halide and extract the memory resources as well as necessary hardware computation from the application, we can actually compile any Halide application down to a hardware data flow graph. Then we can use the QIR as an intermediate representation to represent this graph. The remaining question becomes how you run this kind of arbitrary data graph into your hardware. So we look at all those accelerators being built in the past decade, and a lot of them using spatial parallelism. And since we need to run arbitrary data graph into our hardware, we need a reconfigurable hardware. So based on all experience we have and those requirements, we decide to use a coarse-grain reconfigurable architecture, or simply CGRA. For those of you who are not familiar with CGRA, CGRA essentially is an array of tiles. The tile can either be PE or memories. So PE stands for processing elements. You can think PE as a simple ALU unit, which can perform multiplications or additions. Memory tile is essentially a bunch of memory controllers with SR macros. Those tiles are connected together through reconfigurable interconnect, which means you can route an arbitrary signal from one tile to another tile on the chip. Another benefit of choosing CGRA as our base design is that we can start from a very homogeneous CGRA and then slowly improve it to become more specialized and heterogeneous. So we went ahead and used these new methodologies to design our first generation chip, which we call Jade. If you look at the picture on the left, this is the application flow in the Jade chip. At the very beginning, we have application written in Halide, and they get compiled into a QIR data flow graph. And the graph was further mapped into CGI primitives and can place and route it on our chip. So we finished the entire software stack as well as the hardware in a year with a group of grad students. The hardware is built with Genesis 2, which is a hardware generation framework that uses Perl to meta-program the hardware modules written in system Verilog. If you look at the picture in the middle, this is the final layout diagram for the Jade. So we tipped it out in summer 2018, and then we received package parts back in January. So we built a test floor to test the chip, as shown in the picture on the right. The chip is fully functional, as we expected. One benefit of using Agile hardware design is that it forces you to address the problems that you never thought you would encounter, or maybe you didn't think that much during the initial design stage. So this is exactly what happened to us. One problem we kept running into is that the system would break whenever you made a change. So for example, imagine you are P designers, and you want to increase the P performance by add additional input port. This is very straightforward to do in the P themselves. However, now you have to change the mapper because the P instruction changes. You also need to change the interconnect because you can create additional connection box to accommodate the change. You also need to change the software that consumes the bitstream information. We are not very stupid. We knew this problem might come, but the problem is because Genesis 2 is a general purpose framework, it doesn't know anything about our design. So we had, as a designer ourselves, we had to put additional effort to write down the collateral information in the same code. So if you look at the picture here, the top section is the hardware disk implementation. The bottom section shows the code we write to generate collateral information. At the very beginning, we're very careful. So those two sections are very close to each other. But as design complexity grows, those two sections drift apart. At the end, it's actually more than 200 lines. As you can imagine, you had to keep a memory map of where the things are. And when you make a change, you had to go through all those places to make sure that the changes propagate through the entire system. And this is very difficult to manage in a large design. Our solution to that is to develop a domain-specific language, or DSLs. So why choose DSLs? First, we want generators to be the spec of design that produce both RTL and the consistent API for downstream tools to query. This is what we call a single source of truth. One problem we realized is that generating arbitrary hardware from arbitrary high-level spec is a very difficult problem. But we can divide the problem into generating a specific type of hardware, such as ALUs and interconnect. This kind of division of problem makes the problem more trackable. At this point, you probably ask, designing DSL sounds very complicated. Why don't you have a specialized program that can generate both RTL and collateral? Or even better, have a program to consume your spec and generate all the stuff. But whatever you do, at this point, like I said, because general purpose framework doesn't work, you always have to inject a domain-specific knowledge into a program. So at this point, you're essentially creating DSL. So we just want to solve this problem in a very clean fashion. Just to show you how a DSL works in our system. So peak is a Python-embedded DSL for describing ISA and the functional model of PE. If you look at the picture on the right, peak can produce RTL, test harness, and functional model. Each primitive in peak has a precise formal semantics, which means you can derive the map readout rules automatically. And as a plus side, you can even formally prove that the mapping process that maps application to peak instructions is actually correct. So here's an example to show you how peak works. The main idea behind peak is to have multiple interpretations of the same peak object. If you look at the code example on the left, that describes a very simple P program that contains some ALU ops and their functional semantics. Because peak is embedded in Python, you can just run this program and obtain a functional model. But if you evaluate the same program in Magma context, you can produce RTL. Magma is the hardware generation framework we have for peak. Because peak has formal semantics, if you evaluate peak in the SMT context, you can derive the symbolic representations we can use for generating mapper rules. This is just an example to show you how a DSL can be used as a single source of truth. Like peak, we have two other DSLs designed for each component of CGIA. So we have Lake for memory and Canal for interconnect. Like peak, Lake can produce memory mapper rules automatically from an arbitrary memory descriptions, and the kernel can produce place and row graph for the application, for downstream tool to map the application to map it into CGI. Those three DSLs interact with each other and serve the purpose of separation of concern. In the example I just brought up, if you make changes to a PE, because each DSL has a queryable API, kernel can introspect the peak object and realize, OK, now you have additional input port. I will create an additional connection box for you automatically. So those kind of interaction avoids any human in the loop. Just help you memorize the naming convention we have here. If you look at a picture on the right, peak is like the top of mountains, and lake is like the memory reservoir, and the canal is like the river that connects things together. Those three DSLs sit on top of a new generation framework, which we dub as next generation generators, or simply next gen. You probably laugh, why a new generation framework? Another problem we also ran into is that due to requirement of physical design, sometimes we had to change logical implementation because the physical hierarchy always followed the logical one. One common solution for that is to change how the generator produces RTL, and which we did. But as we did more changes to the generators themselves, we found out two problems. First, the generators themselves becomes very brittle because we add algorithmic changes to it, and the generator becomes very dependent on a particular technology. And sometimes those changes are very useful for other designs. Because we embedded those changes in the generator themselves, those changes are not reusable at all. So our solution for that is to acknowledge that sometimes the logical design needs to go through many passes to reach the final design. So we should have a framework that allows those kind of passes or transformations to transform our logical implementation to desired state. Just to help you contextualize the problem, in the picture here, there's a simple CGI design where each tiles are wired together from the global controller in a fan-out fashion. During the physical design phase, you want to change how those wires are wired together due to, for example, timing constraint. But we want a certain transformation happening in this design that keep it separate from the initial logical design phase. So we expanded this idea and developed a new framework we call Gemstone. So Gemstone is a structural generator that allows multiple passes to create RTL design. Gemstone has a set of well-defined primitives on circuit objects, such as add or remove ports and instantiation generator circuits. The main idea behind Gemstone is to allow multiple passes to change RTL and generate non-RTL collateral. If you look at the picture on below, at the very beginning, we have the initial RTL for the logical designer. So we can add one pass to change how the registers are placed in the system. We can also add another pass to change how the global signal are routed. And add another pass to insert the power domain switches into interconnect to allow the tiles to be turned on and off during configuration or even when the application is running. And of course, we can have a path to extract the floor planning or timing constraints that will be very useful for the physical design. And just to help you understand how the passes work in Gemstone Framework, on the left, we have the global fan-out design. What we can do in this transformation is to remove all the wires first and add additional ports to each tile, and then chain those tiles together in a daisy chain fashion. So this is just an example to show that a path that keeps exactly the same logical description, it will make a huge difference in the physical design, especially timing perspective. This is not a completely new idea, and lots of modern place and route systems are already doing that in a very ad hoc fashion. But those changes typically happen in the physical design backend, and not in generators themselves. So we want a more visibility of how those passes change our generators. That's why we want to develop our own framework. So using these three new DSLs and Gemstone framework, we designed our next generation chip we call Garnet. So Garnet is a more complex and has more component dependency than the first generation JIP chip we have. If you look at the architecture diagram below, especially the bottom right corner, this is a CGI chip that we improve upon J-chip. But we also add more SOC component. If you look at the blocks, like colored in blue, we have a ARM Cortex-M3 chip, we have SRAMs, we have DMA engines, and then we can even talk to a ARM subsystem on FPGA through the core link. This is just an example to show you how we slowly improve our first generation to the next generation. So Garnet chip actually allows application to run the entire application end-to-end. So we re-implement every single thing from scratch, including hardware and software stack in 7 months, and we produce a tape-out-ready design as you see picture on the left. So Garnet is a full-size SoC working RTL simulation. Just to showcase on the spec of the chip, Garnet features a 32 by 16 CGI array, and each P tile can perform either 16-bit or B-float operations. We also have a 4 MB second-level memory that serves as a buffer between the M3 processor and the CGI array. And we also incorporate lots of ARM IPs to make the SoC working. Because this Agile hardware approach, we are still in the process to improve the entire system flow. So we have the first generation chip called Jade, and second generation called Garnet. But this is still an ongoing process, and there are lots of opportunities for us to improve. For example, we can use DSC feedbacks to automatically optimize the design. We can continuously harden the CGI to make it more area and power efficient. So we can add in more complex P instructions or even make the P more heterogeneous. So we plan to tape out another Linux-capable SoC design by the end of next year. And as always, we will continue to polish our toolchain flow, then make the test, and evaluate the entire system all the way through the physical design. Just to answer the question I raised earlier, yes, Agile hardware design is possible. To prove that, we produce 2 chips with a complete software stack and hardware in 2 years. And we'll continue to evolve the hardware and software stack. For those of you sitting in the audience who want to adopt our Agile methodologies in your own company, own team, I think there are 3 major take-home messages. The first is to have a clean interface between hardware and software that allows both of them to be improved together. So in our research, we use Halide and CoreIR as a clean interface between our compiler, our application, compiler, and hardware stack. The second message is to design DSLs for hardware generators, which will make hardware design more trackable and easier to change. So in our research, we developed Peak, Lake, and Canal that generates different components for our CGI. The last message is to have a state generator that allows a separation of concerns between logical descriptions and the physical implementation. So in our research, we developed a framework called Gemstone that allows us to transform logical implementations to the state we desired. At the end, I want to thank all the people who have been involved in this project. The list is very long. I'm not going to read it. Special thanks to our sponsors, especially DARPA DSS program, and our industrial partners. So all our tools are open source at GitHub, and we are very open and happy to collaborate with everyone here. And thank you for your attention, and I'm happy to answer any questions.
Thank you. The floor is open for questions, so any questions? In that case, let's thank the speaker again. Thank you. Okay, so our next speaker is Peter Mattson from MLPerf. He'll talk about machine learning benchmarking. Peter leads the ML performance measurement team at Google Brain. He's the general chair of the MLPerf. Previously, he founded the Programming Systems and Application Group at NVIDIA Research. And he also worked for Stream Processors Inc. and Reservoir Labs. And he holds a PhD from Stanford University. So, Peter?
Good afternoon, everyone. I'm going to talk about MLPerf and the many design challenges we've faced in putting together this benchmark for ML learning. If you don't know, MLPerf is a machine learning performance benchmark suite. We measure how fast machine learning goes. It's gathered broad industry and academic support. We're at about 50 companies now and growing pretty rapidly. MLPerf is the work of many people. It was started as a collaboration between Stanford, Baidu, Google, Berkeley, Harvard. Since then, we've been joined by many great collaborators from NVIDIA, Intel, startups like Cerebras, Microsoft, Facebook, and we'd like more. Got a great team. So why benchmark machine learning? ML hardware is projected to be a very large market. All of these projections are kind of numbers drawn from the sky, but 60 billion in 2025 by a couple of sources. And as Peter Drucker once said, what gets measured gets improved. Benchmarking has this really neat property. It helps align research with development. It helps align engineering with marketing, and it helps align competitors across the industry in pursuit of a clear objective. We all want to make those numbers better. So if you want to design an ML benchmark, you need to answer a series of questions. And these questions apply, some of them apply both to training and inference, and some of them are specific to one or the other category of ML activity. So one of the first questions is benchmark definition. What is the benchmarking task you are going to measure? The next is benchmark selection. Which set of benchmark tests do you want to measure? The next is the metric. What exactly is the measure? ML has a unique challenge in benchmarking in that it's very hard to produce, here's the ML code, compile it for your system, run it, there's your number. Rather, we really need submitters to re-implement the ML algorithm for their particular system. So if we allow them to do this, how do we judge that implementations are equivalent enough to enable us to compare architectures? Some specific issues for training and inference. In training, which hyperparameters do we allow? How do we handle result variance? In inference, what do we do for quantization or retraining? Lastly, once we get our numbers, how do we present them in a fair and useful way? So I'm now going to walk through the design for the training and inference suites and then talk about the presentation. First, let's talk about how we define a training benchmark. It all starts with a data set. Then we use that data set to train a model to a target quality. The big question here is, which model? So we came up with the idea of two divisions. We have a closed division in which the model is specified. For instance, train ResNet on ImageNet to 75.9. This is intended for apples-to-apples comparisons of hardware. We also have an open division where the model is not specified. The open division is intended to encourage innovation in models. This model is faster, or to encourage people to do hardware-software co-design. Now that we know what we think a benchmark looks like, how do we go out and pick out a set? Well, we looked at 5 big categories, the first of which is vision, next of which is speech, third of which is language, fourth is commerce. This requires a little more explanation. Commerce is the things that just kind of make business work. Recommendation, either of things to buy or things to watch. Time series for doing things like defect detection. And lastly is research. These are the things that we're sure they're going to be big someday and we're trying to figure it out, like reinforcement learning or GANs. Once we've looked at sort of this big space and we're trying to pick out the models, the exact models of interest, we look at several ranges of models to choose from. One range is the maturity range. This goes from, we could pick AlexNet for image recognition, right? Everybody could do it. Or we could pick something hot off the presses or relatively hot, like EfficientNet. And our principle here was to try and be cutting edge, but not bleeding edge. What variety of ML model are we interested in? Several different ways of solving the same problem. To do translation, you could use RNNs or you could use attention. And we try and ensure coverage at a suite level. So we may not cover for the same task, but across the suite, we'd like to have some representative examples of different varieties. The last is complexity. How big do we make the model? Less or more weights? For object detection, do we use SSD or mask RCNN? What resolution do we work at? And here we're really starting to try and narrow down and give the market what it wants. So we talk to people and we try and anticipate where the market is going. And the last is practicality. We really can't do it if there's not a public data set. And here we just go with the principle that good now is better than perfect later. At MLPerf, we believe in agile benchmarking. So this is the set of training tasks we started with: 3 vision tasks, 2 translation tasks, a recommendation model, and Minigo. This is a reasonable set, but it's just a starting point. We plan to broaden and evolve this. So we have our models, our tasks. What metric are we going to measure? And there's 2 obvious ones in ML. One is throughput. The other is time to train. So throughput has some advantages. It's easy and cheap to measure. But you can increase throughput at the cost of total time to train. For instance, lower precision or higher batch size will make your throughput better, but they may increase your total time to solution, which is what the user really cares about at the end of the day. So we have gone with time to train. This is the end-to-end time for the model. How long does it take to reach that target quality? This has some drawbacks too. It's expensive because it has to run for a long time. It's high variance. The number of epochs changes from run to run with the same platform and software, but we think it's the least bad choice. In terms of that special challenge I talked about of enabling people to re-implement their benchmarks and have them be equivalent enough for hardware comparison, we feel this is still necessary because there are competing frameworks. There's different architectures support different frameworks, and the implementation still requires some degree of tuning, especially as you try and scale them up. So we have the solution: re-implement things. We require that the models be mathematically equivalent. In particular, the sort of core ML, the network needs to look the same, do the same operations. We do allow some exceptions. We're more flexible around pre- and post-processing type of things. We have to support different numerics. We have a whitelist of other minor differences that are just practical ways of getting this done. But we try for equivalence in the closed division. We also look at hyperparameter tuning. If you have different size systems, you need different batch sizes, and that means different hyperparameters. But some sets of hyperparameters are very definitely better than others. And finding them is hard and expensive, and we really don't want to create a hyperparameter search contest. So we need to balance these 2 things: the need for scalability with not wanting a search contest. So our early solution for the first 2 rounds of our training benchmark was hyperparameter borrowing during the review process. You see someone's hyperparameters, you think they're better than yours, you can use them. And then sort of update your submission before it goes public. A better solution that we're currently working on is the idea of a hyperparameter table. This is a table that would map batch size and numerics to the hyperparameters you should just use. We don't know whether that's possible. We've got a lot of data, and we're trying to figure it out. Another challenge is variance. ML convergence is high variance. Models take different number of epochs over different runs. Exactly the same setup, different random weight initializations, different number of epochs. So our solution is to run each benchmark multiple times, drop the low and high scores, and average the rest. This is kind of a solution. Unfortunately, it's expensive. And so we can't really run it 1,000 times. So we accept some fairly high margins of error. I would say our vision benchmarks are plus or minus 2.5, very roughly. Our other benchmarks are maybe plus or minus 5. Let's talk about inference now. So again, same series of problems. How do we define a benchmark? What benchmarks do we select? How do we define our metric? So to define an inference benchmark, we start with some inputs. We run them through a trained model. We produce some outputs. We have the same question. Do you specify the model or not? We give the same answer. We've got 2 divisions, one where we do, one where we don't. But this is too simple for inference. Inference is really used in 4 different scenarios. First of all, there's a single stream of inputs. For instance, doing something on your cell phone. Then there's multi-stream. This could be automotive. You've got multiple cameras. You're trying to process them all in parallel. Then we've got server. You've got some Poisson distribution of arriving tasks or arriving inputs, and you need to process them within a latency bound. And the last is offline. Big stack of inputs, produce big stack of outputs as quickly as possible. These are the benchmarks we selected. Sort of similar criteria to training. Except I will say that in Inference, we really prioritized something that everyone would find reasonably accessible for our first round. We have a lot more planned submitters. So we picked things like MobileNet, ResNet, SSD, GNMT, things that people were familiar with. Because we have these 4 different scenarios, we actually have 4 different metrics, one for each of the scenarios. For single stream, it's all about latency. How fast can you process each of those inputs? For multiple stream, we give you a latency bound, and then we ask, how many streams can you support while still meeting that latency bound? How many cameras per chip, for instance? For server, we have QPS, and for offline, we have throughput. Inference also has the implementation equivalence problem. You have some set of inputs running through your system under tests and producing some set of results. Even greater range of software and hardware solutions. We do allow people to re-implement, same mathematical equivalence requirement, and we impose some additional constraints that let us check whether systems are at least basically equivalent. One of those is we require everyone to use a standard set of pre-trained weights in the closed division. The second is we require everybody to use a standard load generator that generates the inputs in accordance with the scenarios, times the processing, validates the results. The special challenge in Inference is quantization and retraining. We supply FP32 weights. Everybody wants something else. They want smaller numerics, FP16, IN8, maybe IN4. So quantization is really a key to efficient inference, but we don't want a quantization contest. This is sort of similar to hyperparameter search. It can give people an advantage. So the question is, in the closed division, can you quantize? Yes, but we insist that you're a principal. You have to describe a reproducible method, no magical quantization. Can you calibrate? Yes, but you must use a fixed set of calibration data. Can you retrain? No. Retraining really opens the Pandora's box, and we're just ruling it out of this first round while we figure everything else out. Then we'll look at it again. We'd like to give people this flexibility, but it's hard to figure out how to do it in a fair way. All right, so that gets us to our results. And now the question is, how do we present those results? You can make a good system look bad or a bad system look good, depending on how you choose to do that. One of the questions is, when you give people the scores, do you normalize them by something? Frames per watt or some such. Or do you provide some scale information, at least something to give people an idea of what's a small system, what's a big system? So let me give you an example of how this works. Suppose I have 2 systems, foo and bar. They each post a time on ResNet. Clearly, bar is the better system. But wait, foo had only 1 chip, bar had 4 chips. So clearly, foo is the better system. But it turns out that that is a really monstrous chip. It consumes a heck of a lot of power. And so bar is actually the better system, right? So results alone lack scale information. They can distort what's really going on. So we need to provide supplemental information. Currently, we provide number of chips. We're working on power. This is very important to keep in mind when reading our inference results. Inference is infinitely scalable. Double the system, double your number, okay? And people will do that because it'll give you a sexy number. Make sure you normalize. Presentation, part 2. So when you have some results, do you summarize them? Do you give a single MLPerf score? Here's 2 systems, different scores on 2 benchmarks. We could give them an MLPerf score somehow. And clearly bar is the better system. Of course, if you want to do translation, in reality, foo is the better system. So in short, our conclusion after some debate was that summaries are easy to communicate and do enable people to do summarization consistently, but they oversimplify. Some vendors want to submit subsets. Other users only care about different subsets. So we don't summarize. If you do, please use weighted geometric mean. Arithmetic mean has traps. Lastly, I'm going to talk about, or next to lastly, I'm going to talk about results. And with results here, I don't mean, this company's hardware is better than that company. What I want to talk about is the impact of benchmarking that we're seeing on our results. Is this benchmark moving the industry forward? So first, let's ask, does it drive performance improvements? So what I'm going to do is show you a comparison of 16 chip systems, the best score on any 16 chip system in versions 5 and version 05 and 06. So here they are, and you see a substantial performance improvement, somewhere around 50% across that 6-month span, same hardware. No one introduced new 16 chip systems in this time, with higher quality targets. On 3 out of the 5 benchmarks, the ones that don't have the big impressive red bars, we raised the quality targets. So I think it's reasonable to assume this is pretty much a 2x speed up on the same hardware across the board. And some of this is because we're getting better at optimizing benchmarks. But some of it is because we are driving everyone to make their software stacks better. And this is value that's passed on to all the users of ML. MLPerf has also been driving scaling improvements, because one of the ways to make systems do more is to make them bigger. But that's challenging. Models don't scale perfectly. So if we look at the number of chips in the fastest closed submission between V05 and V06, you can see quite a jump. We're figuring out how to make the benchmarks run on bigger systems. Again, some of it's benchmarks, but a lot of it is also driving the software stack. 6 months, same hardware. The last thing we try and do is make market choices more transparent. We're trying to get away from, in the same way that Spec did for general purpose computing, from marketing department says one thing, other marketing department says something else. We want to give them a common ground for comparison. If you don't believe me, how about Eric Boyd from Microsoft, or Urs Holze from Google, or the Tech Press, who's now strongly encouraging folks to include MLPerf in their evaluation of hardware options. So what are we going to do next? We've got some interesting future plans. For benchmarking, we really want to develop a benchmark framework. What does this mean? We want to lay out the areas we want to cover, what benchmarks we want to handle in each area, what application or applications we believe are driving each benchmark, identify a set of advisors, not from the vendor side, but from the customer side, for each of these benchmarks, both in industry and research, to help guide direction, to say, you should be benchmarking that model, that's clearly the future. So we want to create a table that has entries like this. This is for vision. We've got a couple benchmarks, some driving applications, some advisors. So here's what a full framework might start to look like. Again, those 5 areas I presented, plus mobile vision, which isn't really interesting in training, but is interesting in inference. For each of them, we'd like to have on the order of 2 benchmarks, lineup applications and advisors. We are putting this together as I speak, so if you are interested in contributing, now is a good time. You can see where we're covering now with V5 and V6 for training and inference. So we've got some ways to go, but we're building. We also want to continually improve our rules and reference code. We really do believe in Agile benchmarking. We launched, we're iterating. We changed the rules quite a bit relative to existing benchmarks as we figure out how to do this right for ML. Makes for an exciting ride, but I think ultimately it's producing a better benchmark. So in training rules, we're really looking at how we figure out the allowed hyperparameters. We're trying to figure out optimizer equivalents across frameworks. We discovered that some optimizers were not the same the last round. We're trying to figure out how to reduce variance. For inference, quantization and retraining is really a struggle for us. We need to figure out a good rule for retraining. Power measurement. Power is hard. We're trying to figure out a sensible approach. We also want to continually make our reference implementations faster and more readable. ML is unique in that I think the reference implementations we use for the benchmark, the things that we say, are you equivalent to this, are not only good for benchmarking, they are pretty good starting points for development, and we will continue to make them better. Lastly, we're in the process of launching a nonprofit called ML Commons. This will be the permanent home of MLPerf, but it will have a larger scope. Its mission is to accelerate ML innovation and increase its positive impact on society. That is to say, a bigger market that does better things for more people. So we're putting together some pieces. Benchmarks. These are the precision measurements of our field. We want to make better large public data sets. These are the raw materials of our field. We want to do better software practices. This is like going from handmade models to assembly line creation of ML software. And lastly, we want to do better at outreach, demonstrating to people the potential of ML, maybe through research challenges. So we've seen this recipe before. It turns out when you put these factors together in a young industry, very good things happen. We would like to help make that happen. We need your help. Please come to MLPerf.org. We got a nice Get Involved page. We'd love to have people join our working groups and contribute. Right now, we're a completely public organization that will evolve when we get to the ML Commons stage, but right now we welcome everyone. We'd love to have you submit results. It's a challenging process, but it's worth it. We are also in the process of recruiting founding members of ML Commons. Many of the core players in MLPerf are going to become founding members of this new organization, but we are looking for more. We want this to be a broad organization, especially going beyond sort of the vendors interested in benchmarking into the customers interested in using ML and making sure that we're serving their needs. So if you'd like to do that, email us, reach out. Let's make ML better. Thank you, and with that, I will take questions.
Thank you, Peter. Okay, please state your name and affiliation.
Okay. So, Kiran Gunam from Western Digital. So do you have any benchmarks that addresses the sparse neural networks?
We don't presently. Some of the challenges are supporting a benchmark is quite a bit of work. And so we need to carefully pick which benchmarks we're going to support. And that's part of the reason we're developing the benchmark framework and the associated sort of timeline roadmap behind that. And so if you think that's important, we'd love to hear more from you. And we could look at whether or not that's something we should include in the roadmap.
Okay, thank you.
Thank you.
Shai Galon, Marvell. Agile benchmarking is quite a novel concept, especially as the effort to optimize the benchmark as you allow seems to require quite a bit of effort on whoever's using the benchmark. How do you make the benchmark useful if you iterate every few months?
So I think our first goal was just to make a benchmark that reflected reality, like the performance real people were getting on these systems, which does right now involve quite a bit of optimization because these codes are complex and you want them to go fast. But we'd like to lower that barrier to entry over time. One of the things we're talking about is trying to make the reference implementations higher performance, so you can do something reasonable while running the reference implementation. Another thing we've had some conversations about is having sub-benchmarks for, say, network or memory system performance that use traces, which is much more tractable.
And the other question, you mentioned that MLPerf does not actually have a standard aggregate score. But people will have the MLPerf score, right? The fact that you don't put it out seems to just open the way for anybody to do whatever they want. And again, you have a standard which is not a standard.
We had one of our best internal debates on exactly this subject. People had different and strong opinions. I think I showed you kind of the pros and cons. It's something we can continue talking about internally and seeing if we can build enough of a consensus to do it. It's just very touchy, especially for the people who want to build, say, this is an ML vision chip, right? Wait, I can't get an MLPerf score? What do you mean? So it's challenging, and we'll have to see whether our approach proves to be the right one in the long term. But like I said, we believe in Agile benchmarking. If we're seeing that people are creating MLPerf scores at random, we will probably try and figure out some way to address that.
Okay, thanks.
Okay, let's thank the speaker again.
Thank you, everyone.
Okay, then the third speaker is Misha Smilyansky from Facebook. He'll talk about the Facebook next generation training platform. Misha is director of AI system co-design group at Facebook. The group delivers high-performance optimization of the key AI services on existing platform, as well as co-design future AI systems at the data center scale. Before joining Facebook, Misha spent 13 years at Intel, first at Intel Parallel Computing Labs, and later as the director of Exascale Software Hardware Co-Design Group. Misha was 2014 Gordon Bell Award finalist. Okay, Misha?
Thank you. Hello, everybody. Thank you for the introduction. I heard that one question to the previous presenter was about sparse benchmarks, sparse machine learning benchmarks. So I hope my talk will satisfy some of this curiosity. In this talk, I'll talk about Zion, Facebook next generation training platform that was co-designed for various workloads, most importantly, Facebook sparse workloads. And as a co-design, that was basically a very collaborative effort that involved a great many teams at Facebook, spanning a wide range of expertise from networking to computer system design to AI infrastructure to machine learning. So let me start with some motivation. So this slide actually shows a pretty standard simplified view of the training workflow, starting with the data, with feature engineering, training, evaluation, all the way to deployment. It looks simple, but the resources and the system requirements that are needed in order to power this pipeline have been growing significantly. Just to give you some example about machine learning pipeline data growth at Facebook. So for example, in 2008, if you take the entire data warehouse, 30% of this warehouse was used for training, and today it's 50%. Now, if you combine it with the fact that the size of the warehouse has doubled in the same time period, you can easily see that ML data has grown in almost 3x in just 1 year. Another aspect is that in 12 months period, the number of ranking engineers, actually the people who are running, experimenting with new models, trying new hyperparameters, exploring, has actually increased by 2x. And the number of workflow trained and compute consumed by workload increased by 3x. All of those things, they actually place a significant strain, significant demand on system. Specifically, it strains some of the key system aspects of the data center, such as memory, compute, storage, and network. In addition to that, as I mentioned, ML engineers who are experimenting and trying new models, they expect to do it in a very agile form. They need developer efficiency and flexibility from the platforms they're using. It's not only speed, but it's also ability to run on board new models, new operators, iterate quickly over various problem hyperparameters, and deploy to production as quickly as possible. Those things together, the system, the challenges to various data center aspects, such as compute, storage, and network, as well as the developer efficiency requirement, they put a significant strain on the conventional data center infrastructure. It's very difficult to scale. And so that actually motivated us to consider design of the software-hardware co-design of the next generation training platform. So software-hardware co-design has been a very popular word in the last 5, 6, 7 years. And it was also popular before in HPC domain and before that in embedding system design. But one thing that kind of remains important is the workload. You're co-designing for some workload that you have in mind. So with that said, let's take a look at what are the major AI services that Facebook has. There are actually, if you characterize them at a very high level, there are 3 of them. There is ranking and recommendation, which basically are personalization services used in newsfeed and search. There is a computer vision, which includes image classification, object detection, video content understanding, and language models, which include translation and content understanding. One thing to note that among all of those systems, recommendation models, the personalization recommendation models, are among one of the most important models. They're used really, really heavily. So our co-design for the next generation training platform focused on those models. And the other models, they actually are nicer. They have higher arithmetic intensity. They're a little bit easier. And so we thought that if we are able to deliver a good balanced platform for recommendation model, it also performs well for other models as well. So let me start with the deep learning recommendation models, or effectively those are, as somebody earlier referred to them as sparse models. What are those models? Those models are used for recommendation. Basically, you have a user, you have some set of items that user wants to interact with, and then the recommendation, the deep learning recommendation model helps to choose the set of items that user is most likely to interact with. And the features that are fed to those models are the features that represent the user and the item. And some of them are dense, but many of those features are really sparse categorical features. Right? They belong to a set of discrete values or categories. It can be, say, number of user pages, right? Like user pages, right? Or the friends that you're connected to. So because those features are categorical features, the deal is that they need to be represented numerically in some form in order to be trainable, in order to be able to use as part of a machine learning model. And so they are actually embedded into small dimensional vectors called embedding vector using so-called embedding table lookups. Now, once those sparse and dense features are embedded, and you get basically the embedding vectors, which represent the information in each of those features, you perform some kind of interaction, second order or higher interaction between those features. You typically feed the result to some top-level neural network, maybe MLP, which stands for multi-layer perceptron, and then you may have a sigmoid function that would, compute the probability of user interacting with that item. One thing about those models, and those are actually really the sparse models in the sense that embedding lookups are sparse because a given user will not interact with every categorical feature, right? It will interact maybe with a small subset of them. There are a billion people on the planet, but you are not connected to all billion people, more than billion people, the last I've heard. So those models, they're actually quite expensive in terms of resource requirements, and they strain pretty much every part of our infrastructure, from fabric to memory capacity, bandwidth to communication and computation. So I will talk about those in a little bit more details. So first of all, starting with the embedding tables. The embedding tables are very large. As I said, the number of categories can be quite big, right? So in order for you to represent those categories, you need to be able to have a large size embedding table, and the sizes can be tens of the gigabytes. The accesses to those embedding tables actually are pretty irregular, and they have a very low arithmetic intensity. For all practical purposes, this is your sparse linear algebra operation, okay? Then the ways that we train those models, we explore model-level parallelism. So embeddings are mapped to different compute devices, as shown on the left here, but embeddings happen to be different sizes. So in order to get a good load balance, you have to shard those embeddings among multiple devices, like by splitting the embedding tables as shown and right here, to get a better load balance and utilization. So training, the other part of the network, as I mentioned, is a multi-layer perceptron. And this is much more familiar with many people here, to many people here. The parallelism that is exploited here is model or data parallelism, right? And updates can be either asynchronous, which is usually done via sharding the model among some parameter servers, or synchronous, which can typically be done via distributed all-reduce computation. And one thing which is also interesting about those operations is that those are matrix multiplication, fully connected layer, perhaps with some nonlinearity sprinkled between them. But those are dense, irregular computation, but they're tall and skinny, right? Especially for small batch sizes. So getting good efficiency on those models is important. So if you put it all together, if you say, okay, you have embeddings, you have the multi-layer perceptron, and if you partition them and train the entire model, what happens, the embeddings are partitioned using data like model parallel partitioning and are trained for a full batch. And then MLPs are partitioned using data parallel approach, and each of those devices here are trained for a sum batch, so for a sub batch. So in order for you to perform the interaction, each of the devices at the bottom would require basically to get the parts of the embedding from each and every processor at the top, which actually results in an all-to-all communication. So you really have at least two communication primitives, which are expensive, and those are all-to-all and all-reduce, which are fundamental to distributed training of those models, okay? So now that we understand the workload, we understand it, computational requirements, and we understand the algorithm, one of the questions that we ask, how do we design or co-design the system that is balanced with respect to that particular workload that allow us to achieve good high performance and good efficiency. And so here came Zhang. I'm going to go step by step over different features of Zhang and show how those features address some of the challenges with compute memory bandwidth fabrics that we discussed earlier. So Zhang is effectively started, at the basis, it's an 8-socket system where you have an accelerator connected to each of the CPU sockets, 8-socket CPU system. You have an accelerator connected to each of the sockets over PCIe lanes. In our design, we expect that both CPU and accelerator support bfloat 16, as was discussed yesterday by Google and also validated by our internal simulations. The bfloat 16 is actually a really good drop-in replacement for FP32 in some, but not all cases. There are parts of the model that could not be trained using bfloat 16, but those are the embedding table lookups, so they're on a different device. So yes, so we have bfloat 16, and for memory, to address the memory bandwidth and capacity, we actually provided high capacity, low bandwidth DDR memory and a CPU in the order of terabytes, and low capacity, high bandwidth memory on an accelerator in the order of 100 gigabytes to address the memory capacity and bandwidth at the same time, right? So for communications, the system actually has two interconnects, and they're disaggregated. You have a CPU fabric, which is effectively a cache-coherent UPI fabric that is organized as a twisted hypercube, that it has low diameter, good bisection bandwidth, and it has an interconnect between the accelerators, okay? And I'm going to talk about that interconnect a little bit later in detail. So the YAN system, for all practical purposes, it's a fat supernode, right? And but we have a provision this system to be able to scale it out. So we actually have NICs attached to each of the CPUs, and the system can be you have 100 gigabit NIC per CPU, so the system can scale out this way. There are other ways to scale it as well through point-to-point via accelerators and so on. So one thing about our design is it's a modular design. So we actually started with a dual socket motherboard module that contained two CPUs. And we put them together through the backplane and get an 8-socket system. And those are different modules, so they can be serviced separately, which is good for serviceability. Then we also have the OCP accelerator module for accelerator, which I'm going to talk, it's an OEM for short. I'm going to talk about it in more details a little bit later. And we put 8 of them together in an 8-accelerator system. Now we take 8-accelerator system and 8-socket system, we combine them together in different chases, and we get a Xeon system. And you see the black cables running along the edges. Those are the PCIe cables that connect 8-socket system with the 8-accelerator system. So this shows a summary, kind of a high-level platform, a little bit more detailed platform architecture diagram. You see 4 motherboards at the top. You see 8 accelerators at the bottom. What's interesting is those accelerators are connected through the PCIe switches. And the switches are interconnected themselves. That gives us an extra flexibility. I'll talk about it again in a couple of slides. So as I promised, I want to talk about the OCP accelerator module. So when we were co-designing the system, the questions that we asked is, what accelerator do we use? There are a large number of accelerators available, but we have limited resources to enable those accelerators. So to address this, our solution was to create the OCP accelerator module, and Facebook led an effort in the industry to enable this module. And the module defined basically vendor-agnostic common form factor. So as long as different vendors follow those requirements, this accelerator could fit into our system and be one of the accelerators. So let me say a few words about accelerator interconnect topology. Again, the challenge was the different vendors come with different topology. Some have fully connected topology, some have hypercube mesh, some may have rings. So how did we enable that? How do we build one physical design that can accommodate? That proved to be quite challenging, but we were able to figure out. So effectively, we created what we call the superset topology, which is basically a fully connected topology with some extra links that effectively is able to accommodate all other topologies. As an example here, let's say we want to be able to accommodate a vendor that has embedded the hypercube mesh. So if you take the superset topology and remove some of the unused links, and then, I know it's not super intuitive, but then if you rotate the accelerators 4, 7, 5, and 6 by 180 degrees, you actually get the topology that is a hypercube. So this is an example how we could enable different topologies. So let's talk a little bit about software flexibility. So one thing about the system is that it's very important from the ML engineers' point of view to be able to quickly onboard and experiment and run new models. And this system actually gives you a flexibility to gradually increase software complexity and performance. So as somebody who is starting using the system with a new workload, then they can start with a CPU 8-socket only. Right? Once they get used to it, and they actually can try running offloading part of the model to the accelerator. For example, MLP, those are pretty simple to offload, those just fully connected layers. Right? As a next step, when the user of the system wants to use more sophisticated features, they can use accelerator high bandwidth memory for embedding as well. And then, because, as we mentioned, the system has a capability to scale out, the next step would be all-out distributed training. So the system is flexible in a way that it creates a continuum of developer efficiency versus performance trade-offs and allows user to exploit them. Of course, as more sophisticated you become, the higher performance you will get. So let me also mention a few words about hardware flexibility. As I said earlier, the system was designed with 4 identical 2-socket modules. And the system can actually be configured based on the workload needs. It can be configured to be up to 4 2-socket system, 1 or 2 4-socket system, or 1 8-socket system. So here is an example of such configuration. For example, we can disable all other modules and have just 2 CPU sockets connected to the 8 accelerators through PCIe switches. And because of the connectivity between PCIe switches, those 2 CPU sockets will be able to access all of those 8 accelerators. So that gives us additional flexibility to be able to reconfigure the system different ways. So let me share a few preliminary. So we are in the process of enabling software on the system, efficient performance. And I want to share some of the results running our production models on that system. Okay, and this is using the CPU only. So starting, the results are relative, and they're relative with respect to 1 socket. Starting with 1 socket, if we enable intra-parallelism, we actually get 5x performance boost on 8 sockets, which is actually not that bad because the workload, as I mentioned earlier, is bandwidth bound because of the embedding lookups. So you cannot quite scale with compute because of the low arithmetic intensity of major part of the workload. Then you also have then the next step was to scale the system to the 8 socket. And if you just if you don't do anything special, the scalability is not great. The scalability is 2x plus. Now, if you optimized all reduced, and because it's a cache coherent system, it requires some optimizations in order to reduce the overhead of coherence. That gets you much better scalability of 26x. And if you perform NUMA-aware allocation, you actually get almost 30x scalability compared to a single socket. So some people might be aware that Facebook actually has a system called Big Basin, which is based on NVIDIA GPUs. It also has 8 GPUs. So the people may ask, how is Zion different from the Big Basin? So here, I wanted to summarize some of the main differences. So first of all, the Zion system has different accelerators, OEM modules, while Big Basin was designed only with a single accelerator. By the same token, Zion can accommodate a richer set of topologies, whereas the Big Basin accommodates a hypercube mesh topology. There is also significantly more bandwidth on a Zion, on the order of terabytes. Less so on a Big Basin. And again, as we mentioned earlier, Zion system is reconfigurable up to 8 CPUs, whereas Big Basin has a single head node CPU, which is dual socket. So that brings me to the end of my presentation. In summary, we co-designed the Zion next generation flexible training platform that helps to address the developer efficiency as well as provide good performance for our important use case of recommendation system. It was co-designed to target demanding sparse workload. And it adopts new vendor-agnostic accelerator module. And as I also mentioned, it's a building block that we can use to scale out to the bigger system. Thank you.
Thank you, Misha. The floor is open for questions. Any questions? OK, then. Thank you. Oh.
Thank you for the talk. I'm just interested in, you have multiple...
Could you introduce yourself?
Oh, yes, Dong Ping from AMD. So you have multiple large embedding tables, and you were talking about you trying to shard them. So when you do the partition and you do the mapping, could you elaborate a bit more, and how do you actually partition the mapping to a number of the memory modules? Do you do it statically, or do you do it adaptively? And what are the criteria that you use in order to have maximize the local access to reduce the amount of the communication that you have there?
Yeah, this is actually a very good question. And this is, so the question was, how do we how do we partition the embedding tables among multiple memory modules, right? So it's basically, it's a graph partitioning problem. And the challenge is that embeddings have different sizes, but more importantly, they also have different frequency of accesses. And that makes it complicated. So one of the ideas that we've been doing in production is to use profile-guided information, understanding the frequency of accesses, and use that to guide the partitioning.
And do you often need to update these tables as well, or this table are basically static?
Need to what?
Updates the table.
Yes, during training, there are also table updates. They're basically require scattering the embedding into those tables, performing read, modify, write.
Thank you.
In the beginning of your presentation, you mentioned about the storage challenges. Did you manage to solve that? And if yes, how?
Can you repeat, please?
In the beginning of your presentation, you told about 3 problems. One of them was storage challenges, network challenge, and CPU challenge. The very first was the storage challenge. Were you able to solve it? And if yes, how?
Right. So the storage is so the question was, at the beginning, we mentioned several problems that we are trying to address. The storage, the network, the compute memory capacity, and memory bandwidth. So the system itself was co-designed to address the last 3 problems. But the storage problem was also addressed because the storage happens over the net. The accesses to the storage happen over the network. The data ingestion for training happens over the network. So we added a large number of NICs to the system to be able to keep pace with the training process.
Thank you, Misha. That was a great talk. I'm wondering whether this sparse embedding lookup, is it a latency problem or is it a bandwidth problem? I understand that there is not much compute in it.
So that's a good question. It really depends. The question is, with many such things, it really depends on relative sizes of embeddings and relative sizes of tables and the sizes of the request. Because typically, if the request has a large number of accesses to the table, you can pipeline them, you can explore memory level parallelism, and you can get to the bandwidth bound. Right? When you partition those embeddings among multiple devices, right, you need to perform effectively all reduce with the data. And depending on the ratio of local computation to the communication, it can become a latency-bound problem.
And is there a room for prefetching? Like, is there enough compute after fetching the embedding lookups that you can hide the latency?
Yes, there is. If the request is big enough, which and contains a large number of sparse IDs, we can typically prefetch. In fact, what happens? The embeddings are short, right? There may be 32 or 64 bytes, right? So the hardware prefetcher cannot quite learn the parent before it starts randomly access moves to another embedding. And so hardware prefetcher actually hurts because it prefetches past the end of the line. So we actually issue software prefetches as well in order to hide latency. And on a CPU, our high-performance implementation buys us maybe 20–30% more performance with software prefetchers.
Thank you.
There is enough distance for that.
Hi, Ian Cuttress in Antec. In your talk, you stated that the CPU had to have bfloat 16 support. Is that correct?
The CPU, sorry, can you repeat?
The CPU has to have bfloat 16 support.
I mentioned that's how we defined our spec, yes.
OK, so can you tell me what CPUs you've currently been using?
Yes, that's a good question. So I'm actually not sure if I can disclose this information. I probably can, but maybe I'm a little bit extra careful. If you look at what's available, there definitely Intel made an announcement about bfloat 16 support in Cooper's Lake, right? And I do want to mention one thing. It's not directly related to your question, that, as I mentioned before, bfloat 16 is good, but we cannot train an entire model in bfloat 16. We actually, when we train embeddings, it requires actually our original, we trained this model in FP32. Getting this model to train in float 16 was actually quite hard, and it required extra tricks like stochastic rounding and so on.
So can you at least say Intel?
Have you trained in int 8?
Can you at least say Intel?
You can say it for me.
Okay. So Kiran from Western Digital, I have a question. Like in terms of the workloads, how general are your workloads? Let's say you have Phaser, you have newsfeed. If somebody is going to build an accelerator for you, can that accelerator be used in other applications, like from other companies? Like what kind of workloads you're running, basically?
That's a good question. Yes, our workloads are general, right? We have video understanding, we have language models, right? Even the recommendation system that I described, they're not really unique to us. There is a lot of good work and publications by Alibaba, for example, that talked about sparse models. There is about recommendation models. There is work by Google and wide and deep or cross and deep network. So those are pretty general models. It's the same as holds true for vision models as well as the language models. So I don't think there is anything specific to us that cannot be reusable in the context of other companies.
Got it. But at the same time, your accelerator is asking to support both vision and the language models. But let's say in some applications, most of the applications may just need only vision. That means, let's say they need to support sparse CNN. But now, if you put a requirement that, okay, it has to support the language modeling, right, it may put an additional overhead in the accelerator. So my question is that not all the companies may have the same diverse workload as you have. And then I think you're probably putting a requirement of training and then all these different models. What I'm saying is this a realistic workload for somebody to sell an accelerator to different markets?
So I think, so that's a good question, right? When you build the accelerator, how do you make it I think it comes to the point of when you build the accelerator, how do you provision it to be more general, right? That it can actually address the requirements of wide set of models. So I want to say that this is a very important question, and it's going to be even more important going forward, because machine learning as a field is becoming extremely diverse in terms of kind of capabilities that people want to experiment with. The framework such as PyTorch with the eager execution mode enables a lot of such new ideas to explore. So being able to build accelerators that has a good provision also for a general purpose computation is very important.
Okay, thank you so much.
Okay, last question.
Hey, Anand Iyer from Samsung. Thanks for the talk and the publications. Your team does great work. So you talked about Zion for training, right? So for inference, does a similar architecture optimization, work? Do you, with the sufficient batching and parallelism, do you see the problem, somewhat similar, obviously, given latency constraints and whatnot for inference?
Yeah. That's a good question. So the question was, so we presented the Zion training platform and whether a similar platform would be good for inference. So this platform can be used for inference, of course, because it has accelerator, it has memory, it has compute, but it's definitely an overkill for inference. For inference, you can do things in a much more energy efficient way. For one, you don't always need FP16 or bflow16. With quantization, you can get a lot of models to work in int8. And so I'm not, Facebook actually, in the last Open Compute Summit announced an inference platform. So I encourage you to take a look at the design and co-design of this platform. Some of the features are similar, but the way that the system was engineered, it was engineered for inference, which has somewhat different set of challenges, including, like I said, the accuracy, less stringent accuracy requirement, different batch sizes, and so on.
Okay, thanks.
Okay, let's the speaker again.
Thank you.